Let's move on. Oh, doesn't want to let me move on. Okay. Yeah. So what is artificial intelligence here? Then we'll deal with machine learning. Well, at some level, artificial intelligence is just the current way of doing stupid things faster with more energy. Lots of the modeling that we can do over the years of taking data in and producing models, it doesn't necessarily use machine learning. It doesn't have to do anything with artificial intelligence and works really well. And it's called either statistics, modeling, or data science if you're a bit more trendy. But there are aspects to modern data-driven approaches that are really very powerful, and we will be using and encouraging the use of many of these in this network. Okay, so what is AI? Well, it really splits for the purposes here into general AI. That's the thing that's going to take over the world. Fortunately, nobody seems to be there yet, so we can sort of park that bit. Narrow AI is applying the ideas of artificial or at least augmented intelligence to specific domains, and that's much more doable. Now, in the area of medical things, expert systems have been around for some time. They've come in and out of favor, but generally capturing the knowledge that an expert can bring to this, capturing it in such a way that it can be applied by more people, has had quite a good run for its money. And certainly I think in modern ways, modern systems, that's coming back in. The problem is you've got to capture the knowledge in the first place, which means you've got to find the experts and work out what they're doing. Actually using modern reasoning, so actually allowing logical reasoning and inferencing going on in these expert systems does mean you can capture a little less, just get the principles, and basically systems can work out a little bit more, and that's much more like an intelligent operation. Again, very powerful, very useful, but time consuming in capturing the information. The approach that has come to the fore recently is to use the sort of data that our previous speakers have been talking about coming in and do what's called machine learning. And basically these are data-driven decision-making systems where you learn the model from the data. This can be in terms of looking at clustering, so the so-called unsupervised learning, where you just look at the data itself. But sometimes you do have some data subset that may be where you know the outcomes, and that leads to the sort of supervised learning, where you train a model based on outcomes you know about, and they use it to look at more general cases. These have all been used enormously successfully in sort of drug design and other areas like that. Reinforcement learning, where actually the systems sort of play itself. This is the sort of thing that comes in the deep mind work I'll allude to in a little bit. There is another example of the type of approaches where the system tries to learn what to do based on trying to achieve an outcome. There are other things like active learning, where you start with what you know and work out what experiment, what measurement should you do next to improve the ability to predict. All ways of generally getting your data and doing something useful with it. Why that's not working today. So one of the big players in this area that I'm sure anybody with any interest in chemistry, biology, and so on has seen is DeepMind's work on protein structure prediction. So given a sequence, can you predict what the structure will be? Extremely interesting advance. They're working through, they're about to publish another, I think, few million structures of proteins. Making that available is really an interesting perspective here. It's the beginning rather than the end of something. It's very good to be able to predict these structures, but a lot more is needed if we're actually going to use that information. But nonetheless, a major advance here in using huge computational power, but using the machine learning approaches to take structural data in and sequence data in other known structural data and predict something for new proteins. It's remarkably effective. So in general, one's taking, as we've seen already in presentations, some sort of chemical biological signature, make some analytical measurement, get some data, and make some predictions. And what I highlight here is we need to map the things we can measure onto the things we would like to be able to measure and we would like to be able to predict. In many cases, we cannot easily make the measurement we would like to make, either because we don't have a technique for it, or because it would be invasive, or perhaps we don't even know what it is that we want to measure. So I might well suggest we have a Rumsfeld principle. Of course, this known unknowns and so on is much older than him, but he's kind of popularized it. And I would say what we have here is things we want to know and know how to measure. No, blood glucose level. We'd like to measure that. We can measure it. We may be even work out how to measure it non-invasively. This is useful in understanding what we should do, for example, for diabetes. There are things we would want to know but don't know how to measure, or at least directly. So can we work out how to take a suite of measurements that we can measure and infer something we would like to know? And then the things that we don't even know that we want to know. but would be useful if we could know them, as it turns out, but we don't even know that. And that's the sort of thing where we make a series of measurements and look for correlations with outcomes, the sort of life expectancy sort of things are there. All of these areas, the machine learning approach to actually link what we can measure to what we might want to know is extremely powerful. But to make the best use of the data, we need an information architecture, and you've seen that discussed already, that we need to collect the data appropriately, and we need to handle it in a form that it can be passed on to those people who want to make the models, and the models need to be passed back to the people making the measurements and making the clinical decisions. This needs a whole infrastructure, and it's something that we need to work out how to support. So one of the major barriers here is data. There's never enough quality data, and quality being the word. You've got to get the data, we've got to have it in a machine readable form, and we've got to know where it comes from, the provenance, the quality, and so on. This is an extremely important aspect to be thought of right from the beginning in all of the systems. But of course, the statisticians would have told you that right from the beginning. Standards already been mentioned. Standards are wonderful, can never have more than enough standards. But the issue of the plugs here just shows you how difficult standards can be. Nonetheless, you might, when we again used to travel, you might have come across some of these plugs that allow you to sockets that take multiple types of plugs. So there are lots of ways around here, but actually trying to agree on some standards would be by far the best. And there are many standards out there that we need to bring together. But overall, one of our problems is that we can't really run AlphaGo, the thing that played Go and played hundreds of millions of games against each other. We can't do that in this way. We don't have enough patience. We can't really afford to make all these measurements. We really need to move on from the big data to small data learning. And in that, use prior knowledge of chemistry, science, biology, and so on in the models to build that in. So essentially what we want is a part of the knowledge in the expert systems and the data brought together to make the models. But overall, we do have to worry about questions of bias. Note the announcement a couple of days ago about checking for the oxygen monitors as to whether or not there's depends on your ethnic background, whether or not they're as effective or not, giving reliable notes, results. Are they calibrated appropriately? Well, that applies to the data, and data bias in the data will give to bias in the models, but models can also be biased themselves even without the data. And so it's essential that the models we build are explainable. We need to be them accountable and reproducible. So the reproducibility means we have to make sure we can describe the models well enough and provide the code, provide the training data and so on, that other people can see what's going on. The explainability means we need to be able to find out why they came to those decisions, what's been going on in there. And these are all really, really important in the applications of machine learning approaches, and not at all easy to be sure about. So what we have is tremendous opportunity using modern developments in computer science, in computational capability and so on, that demands quality data coming in, but we are, as you've seen, being able to measure all sorts of things, and coupling the data with the computation means that we can hopefully find some of the solutions. And as we've seen in the last few years, some solutions it's really important to find really rapidly in terms of both testing and treatment. So thank you very much. Hope that's given you a little bit of a push to think about and ask about questions of what machine learning can do for you. Thanks very much.